July 19th, 1944. A testing ground outside Aberdeen, Maryland. American engineers stood in silence as they watched a German Panther tank roll past their observation post, its Maybach HL 230 engine purring with a mechanical precision they had never quite achieved in their own designs. The captured beast had been shipped across the Atlantic, still bearing the scars of combat and the fading Balkenkreuz on its turret. What began as routine evaluation of enemy equipment would transform into something far more uncomfortable, a technical education that forced American tank designers to confront the limits of their own engineering philosophy. The German Panther wasn't just another enemy vehicle to be catalogued and dismissed. It represented a complete rethinking of armoured warfare that had emerged from brutal lessons learned on the Eastern Front, where Soviet 34 tanks had shattered German confidence and forced a radical redesign of their entire approach to tank development. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The story of how American engineers evaluated the Panther reveals more than just technical specifications and performance data. It exposes the fundamental differences between American and German approaches to military engineering, the cultural assumptions embedded in design choices, and the uncomfortable reality that superior industrial capacity does not automatically guarantee superior equipment. The American team that gathered at Aberdeen Proving Ground in the summer of 1944 expected to confirm their assumptions about German desperation and declining quality. Instead, they discovered an opponent who had solved problems American engineers were still struggling with, using methods American industry wasn't structured to replicate. The Panther that arrived in Maryland carried serial number 212054, captured during the Anzio campaign in Italy after its crew abandoned it with mechanical damage. American recovery teams had found it partially hidden in an olive grove, hastily camouflaged with branches and netting. The fact that German crews had tried to destroy it before withdrawal testified to the value they placed on preventing its capture. Demolition charges had been placed but failed to detonate properly, leaving the tank damaged but largely intact. After field repairs to make it transportable, the 60-ton beast was loaded onto a Liberty ship and transported across the Atlantic to the United States, where it would receive scrutiny more thorough than any German tank had previously undergone in American hands. Aberdeen Proving Ground served as the United States Army's primary testing facility for weapons, vehicles, and equipment. The sprawling complex in Maryland housed ranges, test tracks, ballistics laboratories, and engineering workshops where American military equipment underwent evaluation before entering production. The facility operated under the assumption that American industrial methods, American engineering education, and American manufacturing processes produced equipment adequate to defeat any opponent. The arrival of an intact Panther challenged that assumption in ways the evaluation team did not initially anticipate. The American team assigned to evaluate the captured Panther included automotive engineers from General Motors and Chrysler, military officers with combat experience in North Africa and Italy, metallurgists from university research programs, and civilian specialists in armor, weapons, and automotive design. They approached the German tank with professional curiosity, mixed with a certain condescension born from years of propaganda, emphasizing American industrial superiority and German desperation. The evaluation would systematically dismantle that condescension as the team discovered that in several crucial areas, German engineering had achieved solutions American industry had not matched. The visual impression of the Panther immediately differentiated it from American tank designs. The Sherman tank, which equipped the majority of American armored units, presented a tall, vertical profile with relatively flat armor plates arranged at right angles. The Panther, by contrast, crouched lower, its glacis plate sloped at 55 degrees from vertical, its turret angular and compact. The difference wasn't merely aesthetic. It reflected fundamentally different philosophies about how tanks should survive on the battlefield. American designers accepted that tanks would be hit and relied on armor thickness to stop projectiles. German designers, learning from Soviet 34 innovations, angled their armor to deflect shots entirely, making armor effectiveness a function of geometry as much as thickness. The Panther's frontal glacis plate measured 80 millimeters thick, but when angled at 55 degrees, it presented an effective thickness of over 140 millimeters to incoming rounds. For comparison, the Sherman's frontal armor measured 51 millimeters at nearly vertical angles, providing minimal deflection benefit. American armor-piercing rounds that could penetrate the Sherman's frontal armor at combat ranges simply ricocheted off the Panther's glacis, unable to achieve the perpendicular impact angle necessary for penetration. German engineers had effectively doubled their armor protection without doubling armor weight through intelligent geometry. American metallurgists examining the Panther's armor composition discovered another uncomfortable truth. German armor plate used face-hardened steel with a hard outer surface and a tough backing layer, optimized to defeat the specific types of anti-tank rounds encountered on the battlefield. American armor used homogeneous steel plates of consistent hardness throughout, which simplified production but provided less optimized protection against penetration. The German approach required more sophisticated heat treatment and quality control during manufacture, but produced armor that performed measurably better against anti-tank weapons. The metallurgical analysis revealed that Germany, despite strategic material shortages, was still producing armor of consistently high quality using nickel-chromium-molybdenum alloy steel that American plants could theoretically produce but rarely bothered to specify. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The main armament on the Panther consisted of the 7.5 cm KUK 42L70 gun, a weapon that represented the cutting edge of anti-tank gun design in 1944. The designation indicated a 75 mm bore with a barrel 70 calibers long, meaning the barrel length measured 70 times the bore diameter. This extraordinary barrel length produced muzzle velocities approaching 3,000 feet per second, with standard armor-piercing ammunition, giving the gun penetration capability that exceeded anything mounted on American tanks. At combat ranges of 1,000 meters, the Panther's gun could penetrate 138 millimeters of armor plate. The Sherman's 75 mm gun could penetrate approximately 68 millimeters under identical conditions, less than half the Panther's capability. American ordnance specialists test-fired the Panther's main gun at Aberdeen's range facilities, carefully documenting accuracy, penetration, and reliability across multiple firing trials. The results troubled the evaluation team. The German gun consistently achieved first-round hits at ranges where American tank guns required ranging shots to establish correct elevation. The long barrel and sophisticated recoil mechanism produced a stable firing platform that returned to battery position quickly, allowing faster follow-up shots. Most impressively, the optical sights installed in the Panther's turret provided magnification and clarity superior to American tank sights, allowing gunners to identify and engage targets at extended ranges, where American crews would struggle to even spot enemy vehicles. The fire control system integration surprised American observers, who had assumed that German desperation would result in degraded components and simplified designs. Instead, the Panther featured a commander's cupola with periscopes, providing 360-degree vision, a sophisticated gun sight with range estimation features, and mechanical ballistic computers that adjusted for range and ammunition type. The commander could identify targets, the gunner could range and engage them, and the loader could maintain a high rate of fire through an efficient ammunition layout, all coordinated through an internal communication system. American tanks of the period relied more heavily on individual crew member initiative and experience rather than sophisticated mechanical aids to fire control. The heart of the Panther's mobility was its Maybach HL 230P30 engine, a gasoline-powered V12, producing approximately 650 to 700 horsepower, depending on tune and maintenance condition. The engine displaced 23.095 litres and incorporated overhead camshafts, aluminum cylinder heads, and sophisticated fuel injection. American engineers examining the Maybach engine recognized immediately that they were looking at an automotive design philosophy fundamentally different from American practice. Where American tank engines derived from truck and tractor designs prioritizing reliability and ease of maintenance, the Maybach represented a purpose-built tank engine optimized for power density and performance. The Maybach engine weighed approximately 1,200 pounds while producing 700 horsepower, a power-to-weight ratio American tank engines couldn't approach. The Ford GAA engine that powered later Sherman variants weighed approximately 1,400 pounds and produced 500 horsepower and respectable performance, but clearly inferior to the German design in specific power output. The Continental radial engines used in earlier Shermans were even heavier relative to their power output. German engineers had achieved superior power density through sophisticated engineering, accepting increased mechanical complexity and tighter manufacturing tolerances as necessary costs for improved performance. American automotive engineers who examined the Maybach engine in detail found themselves simultaneously impressed and frustrated. The engineering was brilliant, incorporating solutions to problems like efficient cooling, effective lubrication, and reliable fuel metering that American designers were still refining. But the manufacturing approaches visible in the engine's construction differed fundamentally from American mass production methods. German components showed evidence of extensive hand-fitting and individual adjustment during assembly, techniques that allowed tighter tolerances but required skilled craftsmen and more assembly time. American factories were organized around interchangeable parts and assembly line production, approaches that maximized output but sometimes compromised performance optimization. The Maybach's fuel injection system particularly impressed American engineers. The Bosch fuel injection provided precise fuel metering across the engine's operating range, improving fuel efficiency and power output while reducing maintenance issues associated with carburetors. American tank engines in 1944 still used carburetors, simpler devices that were easier to service in field conditions but less sophisticated in their fuel control. The German injection system required precision manufacturing and careful maintenance, but it delivered measurable performance advantages. The American evaluation team noted that German engineers had successfully implemented technology that American automotive industry considered too complex for military vehicles, challenging assumptions about appropriate technology levels for combat equipment. The transmission system on the Panther represented another area where German engineers had pursued sophisticated solutions to mechanical challenges. The AK-7-200 transmission provided 7 forward gears and 1 reverse gear, all controlled through a regenerative steering system that allowed the driver to steer the tank by varying power to each track. The system was mechanically complex, requiring precision gears and careful maintenance, but it provided exceptional maneuverability for such a heavy vehicle. American tanks used simpler, controlled, differential steering, mechanically less sophisticated but also less capable. The German approach allowed the Panther to execute turns more efficiently, consuming less power and maintaining better speed through maneuvers. American test drivers who operated the captured Panther at Aberdeen noted immediately that despite its 60-ton weight, the tank drove more like a responsive sports car than a ponderous armored vehicle. The steering was precise, the transmission shifted smoothly, and the engine provided abundant power throughout the speed range. By comparison, Sherman tanks of similar vintage felt agricultural, with heavier controls, less precise steering, and more mechanical vibration. The difference in driving experience reflected the different priorities embedded in each nation's tank design. German engineers designed the Panther to be an effective weapons platform operated by trained specialists. American engineers designed the Sherman to be adequately effective while remaining maintainable by minimally trained crews using basic tools. The suspension system on the Panther employed torsion bars, long spring steel bars that twisted to absorb impacts as the road wheels moved vertically. This design provided excellent ride quality and durability while keeping the suspension mechanism inside the hull, where it was protected from battle damage. American tanks used either vertical volute spring suspension with exposed springs and shock absorbers, or horizontal volute spring systems, both of which were mechanically simpler than torsion bars, but also more vulnerable to damage and less sophisticated in their damping characteristics. The Panther's suspension provided noticeably smoother ride over rough terrain, improving crew comfort and allowing the gun to remain on target during movement. Road wheel arrangement on the Panther used overlapping and interleaved wheels, with 8 large road wheels per side arranged so that each wheel partially overlapped its neighbours. This configuration distributed the tank's weight across a larger contact area, reducing ground pressure and improving mobility on soft ground. The design also provided some additional protection to the hull sides, as incoming rounds had to penetrate multiple wheel layers before reaching the hull. But the interleaved wheel design created maintenance challenges, particularly in winter conditions where mud and snow could freeze between the wheels, immobilizing the tank until it thawed. American evaluation teams noted this vulnerability, recognizing that sophisticated engineering sometimes created unexpected operational problems. The fire that American engineers had been told would consume German industrial quality never appeared in the Panther they examined. Every component showed evidence of careful manufacture and quality control. Welds were consistently clean and properly penetrated. Machined surfaces showed appropriate finish quality. Castings were free from obvious defects. The fit and finish throughout the vehicle matched or exceeded American military production standards. This wasn't a desperate vehicle cobbled together from substitute materials by a collapsing industrial base. It was a sophisticated weapons system manufactured to exacting standards by an industrial economy that was still functioning effectively despite years of strategic bombing. The transmission's complexity became fully apparent only when American mechanics attempted routine maintenance procedures during the evaluation period. What would take a Sherman crew perhaps 2 hours to accomplish required an entire day for the Panther, even with experienced mechanics working from captured German technical manuals. The intricate mechanical systems that provided superior performance also demanded significantly more labor and expertise to maintain. American military doctrine emphasized mechanical simplicity, partly because the Army expected to field millions of soldiers with varying technical aptitude, many of whom would receive only basic mechanical training before deployment. The German approach assumed trained specialists would maintain their equipment, a reasonable assumption for a professional military but problematic for the mass conscript Army Germany, fielded by 1944. The Panther's final drive system demonstrated another technical choice that prioritized performance over ease of maintenance. The final drives transmitted power from the transmission to the drive sprockets that moved the tracks, experiencing enormous mechanical stress during operation. German engineers designed the Panther's final drives as compact, high-strength units capable of handling the engine's substantial power output. But this compact design created thermal management challenges, and final drive failures became a persistent problem throughout the Panther's service life. American engineers examining failed final drives from combat-used Panthers could see the engineering logic behind the design, while also recognizing that the thermal loads exceeded the component's long-term durability. German engineers had designed to peacetime automotive standards where occasional component replacement was acceptable, but military service imposed continuous heavy loads that revealed weaknesses in the design approach. The evaluation team's materials analysis revealed that Germany was still producing high-quality steel alloys despite strategic material shortages and relentless Allied bombing of industrial facilities. The armor plates used face-hardened nickel-chromium molybdenum steel that matched American armor specifications in metallurgical composition and mechanical properties. Engine components showed appropriate material selection, with hardened steel used for high-stress parts and aluminum alloys, used where weight reduction mattered. Bearings throughout the vehicle were manufactured to tight tolerances using proper bearing steels. The quality control evident in materials, selection and heat treatment contradicted intelligence assessments, suggesting that German industry was collapsing under bombing pressure and resource constraints. What troubled American analysts most profoundly was recognizing that Germany had designed and fielded the Panther in approximately 18 months, from initial concept to combat deployment. The Panther was developed as an emergency response to the Soviet 34, which had dominated German tanks during the early phases of the Eastern Front campaigns. German engineers absorbed the lessons from combat defeats, redesigned their medium tank completely, solved enormous technical challenges, established production lines, and fielded the new design in combat by mid-1943. By contrast, American tank development followed a more methodical timeline, measured in years rather than months, with extensive testing and gradual refinement prioritized over rapid deployment. The German achievement in compressed development. Time suggested that when necessity demanded, German engineering and manufacturing could respond with remarkable speed and effectiveness. The Panther's optical equipment impressed American evaluators who examined the gun sights, rangefinders, and periscopes throughout the vehicle. German optical manufacturing had long been recognized as world-leading, and the Panther's optics confirmed that reputation. The main gun sight provided exceptional clarity with precise reticle patterns that simplified range estimation and lead calculation. The commander's periscopes offered clear, wide-angle views that allowed effective battlefield awareness. Even the driver's vision blocks used high-quality glass with anti-reflective coatings. American tank optics, by comparison, were functional but less sophisticated, reflecting different priorities in manufacturing and design. German engineers treated optical equipment as precision instruments, requiring specialized manufacturing capabilities, while American Dodgers in production emphasized adequate optical quality achievable through standardized production methods. The interior layout of the Panther revealed thoughtful, ergonomic design that reflected extensive input from combat veterans. The crew positions were arranged to maximize efficiency while minimizing the internal volume that needed armor protection. The loader's position provided excellent access to ammunition storage, with well-designed ready racks near the gun breech. The gunner's station positioned him optimally for sight operation and gun control. The driver's compartment included well-placed controls and adequate visibility through periscopes. The radio operator's position integrated defensive machine gun operation with communication duties. Everything suggested that German designers had carefully considered crew workflow and combat effectiveness, rather than simply packaging components into available space. Ammunition storage throughout the Panther showed similar attention to operational effectiveness. Ready ammunition was positioned for quick loader access during combat. Reserve ammunition was stored lower in the hull, where it was better protected by armor and less likely to be struck by penetrating rounds. The stored ammunition configuration minimized the probability of catastrophic detonation if the tank was penetrated, though it could not eliminate the risk entirely. American ammunition storage, in Sherman tanks, by contrast, often placed ammunition in sponsons along the hull sides, where it was vulnerable to side penetration, a design choice that contributed to the Sherman's unfortunate tendency to burn catastrophically when penetrated. German designers had learned from early war experience that ammunition fires killed crews and destroyed tanks, so they prioritized ammunition protection in their designs. The communication equipment installed in the Panther included sophisticated radio systems that exceeded American tank radio capabilities in several respects. German military doctrine emphasized radio communication between vehicles, enabling coordinated tactical maneuvers and responsive command and control. The Panther's radio equipment provided clear voice communication with substantial range, allowing company and battalion-level coordination across dispersed formations. American tanks carried radio equipment as well, but doctrine placed less emphasis on vehicle-to-vehicle communication and more on following pre-planned operations, reflecting different tactical philosophies about how armored forces should be employed in combat. Fire suppression systems in the Panther included automatic equipment that could suppress engine compartment fires before they spread and destroyed the vehicle. Thermal sensors detected abnormal temperatures and triggered fire suppressant discharge, potentially saving the vehicle and crew. This system represented another area where German engineering had implemented sophisticated solutions to known combat problems. American tanks lacked comparable automatic fire suppression, relying instead on manual fire extinguishers operated by crew members, an approach that was less effective once a serious fire had started. The difference reflected German willingness to accept increased mechanical complexity in exchange for improved crew survivability and vehicle protection. The armor welding quality throughout the Panther showed professional workmanship that maintained structural integrity while minimizing weight penalties from excessive weld material. German welders used techniques that produced strong joints without the heavy reinforcement welds, sometimes seen in American armor production. The welding technology employed in Panther production required skilled welders and careful quality control, but it produced lighter, stronger armor assemblies than less sophisticated welding approaches. American armor production emphasized speed and consistency, sometimes at the expense of optimal weld profiles, reflecting the different priorities inherent in mass production versus craft production approaches. Track design on the Panther used manganese steel tracks with center guides that engaged grooves in the road wheels, providing positive track retention even during violent maneuvers or battle damage. The tracks were substantially wider than American tank tracks, distributing the vehicle's weight over a larger ground contact area and reducing ground pressure. Lower ground pressure improved mobility on soft ground, where narrow tracks would sink and bog down. German engineers had designed the Panther to operate effectively on the poor roads and soft terrain common throughout Eastern Europe, accepting the added complexity of wider tracks and more sophisticated track retention systems. American tanks used narrower tracks adequate for the road networks in Western Europe, but less capable on poor terrain. The educational value that American engineers extracted from examining the captured Panther extended far beyond the specific technical details documented in evaluation reports. The experience forced American designers to confront assumptions about the relationship between industrial capacity and engineering excellence. America possessed vastly greater manufacturing capacity than Germany, could produce tanks in far larger numbers, and could sustain logistical support that Germany could not match. But numerical superiority did not automatically translate to technical superiority in every measurable parameter. German engineers, working within severe constraints, had produced a tank that was superior to American designs in armor protection, firepower, and certain aspects of mobility. This realization created tension within American military and industrial circles about how to respond to the German technical achievement. One perspective held that the Sherman's adequacy combined with overwhelming numerical superiority made redesign unnecessary. American factories were producing Sherman tanks at rates Germany could never match, shipping them across oceans that German forces couldn't threaten, and supporting them with logistics that ensured every tank had fuel, ammunition, and spare parts. Even if the Sherman was inferior tank for tank, American numerical advantage would prevail. This perspective emphasized industrial and logistical strength as the decisive factors in modern warfare, viewing technical sophistication as secondary to production volume and supply chain effectiveness. The alternative perspective, held by many frontline tank crews and some engineering advocates, insisted that technical inferiority cost American lives unnecessarily. Every tank engagement where a Sherman crew faced a Panther reflected the design choices embedded in each vehicle. The Panther could engage effectively at ranges where the Sherman's gun couldn't penetrate German armor. The Panther's armor would deflect many rounds that American tanks fired, while Sherman armor was vulnerable to penetration by German guns. American crews compensated through numerical superiority, tactical coordination, and aggressive maneuver, but they paid in casualties for equipment that was demonstrably inferior in direct combat. This perspective demanded that American industry leverage its capacity to produce not just more tanks, but better tanks that would reduce crew casualties and increase combat effectiveness. The debate about how to respond to the Panther's technical superiority became entangled with broader questions about American military doctrine and industrial policy. American armor doctrine emphasized combined arms coordination, with tanks supporting infantry and calling on artillery and air support when encountering strong opposition. German doctrine increasingly treated tanks as primary combat weapons expected to engage and destroy enemy armor directly. These different doctrinal assumptions shaped design priorities, with American tanks optimized for infantry support missions and German tanks optimized for tank versus tank combat. The Panther's superiority in anti-tank capability reflected its design purpose, while the Sherman's versatility reflected different priorities about how tanks should be employed. American industrial policy had committed to Sherman production at scale, establishing extensive manufacturing networks involving dozens of factories and thousands of suppliers. Changing to a new design would disrupt production, require retooling factories, retraining workers, and redesigning supply chains. The institutional momentum behind Sherman production created strong incentives to continue existing programs rather than pursuing technically superior but disruptive alternatives. German industry, by contrast, had less invested in previous designs and could pivot more readily to new requirements, partly because their smaller industrial base involved fewer facilities and suppliers who needed coordination. Paradoxically, Germany's smaller industrial capacity provided more flexibility to change designs, while America's larger capacity created inertia that resisted change. The technical reports generated from the Panther evaluation circulated through American military and industrial organizations throughout late 1944 and into 1945. The reports included detailed measurements, performance data, material analysis, and comparative assessments against American equipment. Senior officers read summaries emphasizing that while the Panther was superior in certain respects, American advantages in production, logistics, and tactical air support more than compensated for equipment differences. Engineers read detailed technical analyses and recognized sophisticated solutions to problems they were still struggling with in American designs. Frontline tank crews heard rumors about the evaluation and wanted to know when they would receive equipment that could match the German tanks they faced in combat. The Panther evaluation influenced several American development programs that were already underway during the evaluation period. The 26 Heavy Tank Project, which would eventually become the M26 Pershing, incorporated lessons from analyzing German tank designs, including the Panther. The Pershing featured a 90mm gun with substantially better anti-tank performance than the Sherman's 75mm, thicker frontal armor with improved angular design, and a more powerful engine. While not directly copying the Panther, American designers clearly absorbed lessons about the importance of firepower and protection in modern tank combat. The Pershing entered service in limited numbers during the final months of the European War, too late to significantly impact the conflict's outcome, but providing a foundation for post-war American tank development. The captured Panther's influence extended into post-war American tank design philosophy, shaping development of vehicles like the M46 pattern and subsequent designs. American engineers recognized that Cold War armored combat would likely involve facing Soviet tanks that incorporated design features similar to the Panther, including sloped armor, powerful guns, and sophisticated fire control. The technical education provided by examining captured German equipment helped American designers understand what characteristics would be essential in future tank designs, even as they maintained distinctly American approaches to reliability, maintainability, and production efficiency. The psychological dimensions of the Panther evaluation proved as significant as the technical findings, though they were documented less formally in official reports. American engineers who spent months examining the captured tank developed a grudging respect for their German counterparts, recognizing the sophistication and competence evident in every system. This respect complicated the wartime narrative that portrayed German engineering as either brilliant but evil or declining into desperate improvisation. The Panther represented neither extreme. It was simply excellent engineering applied to military requirements by competent professionals working within their nation's industrial and strategic constraints. The recognition that enemies could be both morally wrong in their cause and technically competent in their work created cognitive dissonance that some evaluators found difficult to reconcile. The mechanics and technicians who maintained the Panther during testing developed their own perspective on German engineering philosophy. They appreciated the performance that sophisticated systems delivered while simultaneously cursing the maintenance burden those same systems imposed. A transmission that provided 7 smooth shifting gears and regenerative steering was wonderful during operation, but nightmarish when it required service. An engine that produced impressive power, though from reasonable displacement, was magnificent until it needed major maintenance requiring extensive disassembly. The German approach consistently prioritized operational performance over maintenance convenience, a choice that made sense for a peacetime military with professional maintenance personnel, but created serious problems for a wartime military requiring rapid repairs under field conditions. The test drivers who operated the Panther on Aberdeen's test courses came away with mixed impressions that reflected the complexity of evaluating military equipment. On smooth surfaces with good traction, the Panther was a joy to drive, with responsive controls, excellent visibility, and impressive power delivery. On rough terrain or soft ground, the wide tracks and sophisticated suspension provided mobility that exceeded comparable American tanks. But the drivers also noted that mechanical reliability was inconsistent, with various systems requiring attention more frequently than equivalent. American equipment. The drivers recognized that they were operating a combat-damaged tank that had received field repairs and then sat unused for months before evaluation, so some reliability issues reflected the vehicle's history rather than inherent design flaws. Nevertheless, the experience suggested that German engineering sophistication came with reliability costs that American designs avoided through simpler approaches. The ballistics testing conducted at Aberdeen provided quantitative data about the Panther's combat capabilities that confirmed what frontline troops had reported from combat experience. The Panther's gun could penetrate the Sherman's armor at ranges approaching 2,000 yards, while the Sherman's gun could only penetrate the Panther's frontal armor at ranges under 500 yards, and even then only if the shot struck squarely rather than at an angle. This fundamental imbalance in effective engagement ranges gave the Panther an enormous tactical advantage. In open terrain where long-range fire was possible, American tanks needed to close to point-blank range or maneuver for flank shots to effectively engage Panthers, tactics that exposed American crews to additional risk and required numerical superiority to execute successfully. The armor penetration testing revealed another uncomfortable truth about American anti-tank ammunition. The armor-piercing rounds produced for the Sherman's 75mm gun were adequate against earlier German tanks, but marginal against the Panther's thick, well-angled armor. Even at close range, many hits on the Panther's frontal armor failed to penetrate, with rounds ricocheting off the sloped glacis plate or shattering against the face-hardened armor without achieving penetration. American ammunition designers had optimized rounds for reliable performance against moderate armor, prioritizing consistent manufacturing quality over maximum penetration capability. German ammunition, by contrast, showed evidence of sophisticated metallurgy and careful quality control aimed at maximizing penetration against the heaviest armor expected in combat. The evaluation team conducted mobility testing on various terrain types to assess the Panther's cross-country performance. On firm ground, the tank demonstrated excellent speed and maneuverability, with the powerful engine providing strong acceleration and the sophisticated transmission allowing smooth gear changes throughout the speed range. On soft ground, the wide tracks distributed weight effectively, allowing the Panther to traverse terrain where narrower tracked vehicles would bog down. But the interleaved road wheel design created problems in muddy conditions, with thick mud packing between the overlapping wheels and sometimes freezing overnight in cold weather. Test crews had to spend considerable time cleaning packed mud from the suspension, confirming reports from German crews about this persistent problem with the design. The cold weather testing proved particularly revealing about the Panther's operational characteristics under adverse conditions. The Maybach engine required careful warm-up procedures in cold weather, with German manuals specifying extended idling periods before placing loads on the engine. The fuel injection system could be temperamental in extreme cold, requiring priming procedures that were more complex than carburetor-equipped engines needed. The transmission required specialized cold-weather lubricants to function properly at low temperatures, and even with proper lubricants, the transmission was stiff and difficult to shift until it reached operating temperature. American tanks with simpler mechanical systems generally proved more tolerant of cold-weather operation, though they too required cold-weather preparation and suffered performance degradation in extreme conditions. The evaluation's final reports, compiled and distributed in early 1945, provided comprehensive technical documentation of the Panther's characteristics, along with tactical recommendations for American forces encountering Panthers in combat. The reports confirmed that the Panther was superior to the Sherman in direct combat, particularly at range, but also noted vulnerabilities that could be exploited through proper tactics. The reports emphasized that American advantages in numbers, logistics, air support, and combined arms coordination more than compensated for the Panther's technical superiority. The conclusion reflected institutional priorities that valued maintaining production momentum over disrupting established programs to pursue technically superior but operationally uncertain alternatives. The officers who read the evaluation reports and compared them with after-action reports from combat units recognized that crew casualties had strategic implications beyond immediate tactical outcomes. Every experienced tank crew lost represented months of training, investment, and combat knowledge that couldn't be rapidly replaced. The Sherman's vulnerability to German tank guns meant that American tank crews suffered disproportionately high casualties compared to their German opponents in tank versus tank engagements. While American industrial capacity could replace destroyed tanks within weeks, replacing experienced crews required months of training time. The human cost of equipment inferiority, though difficult to quantify precisely, influenced post-war thinking about the importance of technical excellence in military equipment. The strategic bombing campaign against German industry had reduced Panther production below planned levels, but had not prevented Germany from manufacturing the sophisticated tank throughout 1944 and into 1945. German factories produced approximately 6,000 Panthers during the war, despite relentless Allied bombing, dispersed production across multiple facilities, and continuous material shortages. This production volume, though modest by American standards, demonstrated that Germany retained substantial industrial capability even as the strategic situation deteriorated. American intelligence analysts who reviewed production data alongside technical evaluation results recognized that German industry was more resilient than bombing assessment reports had suggested, maintaining quality standards and sophisticated manufacturing capabilities despite severe operational constraints. The maintenance requirements documented during the Panther evaluation highlighted fundamental differences between German and American approaches to military logistics. German doctrine assumed that tanks would rotate through depot-level maintenance facilities, where skilled technicians could perform complex repairs using specialized equipment. American doctrine assumed that most maintenance would occur at field level, using basic tools and general-purpose mechanics, minimizing dependence on rear area facilities that might be unavailable during rapid advances. The German approach allowed more sophisticated equipment but created logistical vulnerabilities when depot facilities were destroyed or became inaccessible. The American approach sacrificed some technical performance for improved operational availability and reduced logistical dependence. The captured Panther's fate after evaluation concluded reflected the military's assessment of its value. Rather than preserving it for historical purposes, the tank was eventually scrapped for materials, with certain components retained for continued testing and some parts distributed to training facilities for technical instruction. The decision to scrap rather than preserve the vehicle indicated that military authorities viewed the Panther primarily as intelligence material rather than as historically significant equipment worth preserving. This utilitarian perspective was common during and immediately after the war, when equipment was valued for operational or educational utility rather than historical significance. Only years later would historians and museum curators recognize the value of preserving examples of significant military equipment, by which time many captured vehicles had already been scrapped. The technical intelligence gathered from evaluating the captured Panther contributed to broader assessments about German military capabilities and industrial resilience. Intelligence analysts had predicted that German industry would collapse under bombing pressure, producing increasingly inferior equipment from substitute materials using forced labor. The Panther evaluation contradicted this narrative, demonstrating that Germany retained the capability to produce sophisticated, high-quality military equipment despite strategic bombing and material shortages. This recognition forced intelligence agencies to revise their assessments of German industrial capacity and acknowledge that equipment quality remained high even as production volumes declined. The revised intelligence estimates influenced strategic planning for the final campaigns of the European war, with commanders recognizing that German forces would remain formidable opponents, equipped with quality weapons, despite their deteriorating strategic position. The American tank crews who learned about the Panther evaluation through informal channels expressed frustration that the military's response to German technical superiority emphasized tactics and numerical advantage rather than equipment improvement. Crews understood intellectually that American industrial capacity could produce more tanks than Germany, but they experienced combat from inside individual tanks, where numerical advantage provided limited comfort against technically superior opponents. The perception that military leadership prioritized production efficiency over crew survivability created morale challenges that required careful management by unit commanders. The eventual deployment of M26 Pershing tanks in limited numbers during early 1945 provided tangible evidence that American industry could produce tanks comparable to German designs, improving morale, even though too few Pershings reached frontline units to significantly impact combat outcomes. The post-war careers of engineers who participated in the Panther evaluation reflected how the experience influenced American military vehicle development. Many evaluators joined post-war tank development programs, bringing knowledge gained from examining German equipment to bear on new designs. The M46, Patton, M47, and M48 medium tanks that equipped American forces during the early Cold War incorporated lessons learned from German tank design, including improved armor angles, more powerful guns, and sophisticated fire control systems. American designers maintained their emphasis on reliability and maintainability, while incorporating German innovations in firepower and protection, creating a distinctly American approach to tank design that balanced multiple priorities rather than optimizing single characteristics. The Soviet Union's post-war tank development benefited more directly from German technology than American programs did, with Soviet designers explicitly incorporating Panther features into designs like the T-44 and T-54. Soviet forces captured numerous Panthers during the war's final campaigns and evaluated them thoroughly, reaching conclusions similar to American assessments about the sophistication of German engineering. Soviet designers, less constrained by existing production investments than their American counterparts, more readily adopted German design features, including sloped armor, powerful guns, and torsion bar suspension. The Cold War competition between American and Soviet tank designs thus reflected not only direct rivalry, but also different approaches to incorporating lessons learned from German wartime engineering. The historical significance of the Aberdeen Panther evaluation extends beyond its immediate wartime impact to encompass broader lessons about the relationship between industrial capacity, technical excellence, and military effectiveness. Germany demonstrated that constrained resources could still produce technically excellent equipment through sophisticated engineering and efficient resource utilization. America demonstrated that abundant resources could overcome specific technical disadvantages through overwhelming production volume and comprehensive logistical support. The war's outcome vindicated the American approach in aggregate, with numerical superiority and industrial capacity proving decisive despite technical inferiority in specific equipment categories. But individual engagements often favored technically superior equipment regardless of broader strategic advantages, creating the tactical strategic disconnect that made equipment evaluation politically sensitive. The engineering philosophy differences revealed by comparing the Panther and Sherman reflected deeper cultural differences between German and American approaches to industrial production. German engineering tradition emphasized craftsmanship, precision, and technical sophistication, accepting complexity as necessary for achieving superior performance. American engineering tradition emphasized simplicity, reliability, and producibility, accepting some performance limitations as necessary for achieving production volume. Neither approach was inherently superior. Each reflected rational responses to different constraints and priorities. The war demonstrated that America's approach was better suited to global industrial warfare, requiring sustained production over years, while Germany's approach was better suited to producing limited quantities of superior equipment for shorter conflicts. The lessons learned from evaluating captured Panthers influenced not only tank design, but broader American thinking about military technology development and acquisition. Post-war military planners recognized that technical excellence alone couldn't guarantee victory, but technical inferiority created unnecessary casualties and reduced operational effectiveness. The challenge was balancing competing priorities: technical performance, production efficiency, reliability, maintainability, cost, and schedule. The Panther evaluation provided a concrete case study illustrating these trade-offs, showing how different design choices reflected different priorities and produced different outcomes in combat. American military acquisition programs increasingly emphasized comprehensive evaluation of competing priorities rather than optimizing single characteristics, an approach directly influenced by lessons learned from wartime equipment evaluation. The story of American engineers examining a captured Panther ultimately reveals fundamental truths about how nations approach military technology development. Technical sophistication matters, but so do production capacity, logistical support, tactical doctrine, and strategic context. The best equipment in isolation may not be the best equipment within a complete military system optimized for sustained warfare. Germany produced technically superior tanks but couldn't produce them in sufficient numbers, supply them adequately, or employ them within a sustainable strategic framework. America produced adequate tanks in overwhelming numbers, supported them comprehensively, and employed them within a strategic context that leveraged industrial advantages. The evaluation at Aberdeen documented German technical excellence, while simultaneously demonstrating why technical excellence alone couldn't change the war's outcome. The lessons learned shaped American military technology development for decades afterward, influencing how engineers balanced competing priorities in designing equipment for an uncertain future. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.